Yes, I need a comment.
He will take it. Okay, so let me welcome Dorian Schur to talk about the discontinuity and our aspects of it.
So thank you very much, and let me start by thanking the organizers for inviting me to participate in the program. It was a real pleasure for me being here. And it's a pleasure for me to give this talk about isoperimetric inequalities and the Robin boundary conditions, because the origin of this problem and solution, in fact, is 3 years ago in the program in Berkeley, in the free boundary program, where Catherine Bandel in the introductory conference spoke about Robin boundary conditions, and she mentioned an open problem. And then I will give now the solution. So my co-authors here are Alessandro Giacomini from Brescia and Stefan Luckhaus from Leipzig. We work independently on some aspects, but different aspects of this problem. And let me start and explain what is the problem. This is a so-called isoperimetric inequality. And these kind of questions, which is well known, like for example, for the Dirichlet-Laplacian, the famous Faber-Kran inequality, which states that among all domains of prescribed measure, the ball has the minimal first Dirichlet eigenvalue of the Laplacian. But here, the problem is slightly different because we want to raise the same question, but instead of the zero boundary condition, to put Robin boundary condition. So let me state the problem. We give a positive beta, and for any smooth domain omega of Rn, we want to solve minus Laplacian u equal to the eigenvalue nu here u, and the boundary condition, which is du over dn plus beta u is 0. And if you want to look to the spectrum, provided that omega is enough smooth, assume Lipschitz, then you have a spectrum consisting of eigenvalues, and the first one is given by the minimization of the Rayleigh quotient that you see here. For every function u in h1 of omega, you minimize the L2 norm of the gradient plus beta, the L2 norm of the function, of the trace of the function on the boundary, divided by the L2 norm of 4. And this gives you the first Robin eigenvalue of the Laplacian. It corresponds an eigenfunction here, u, which really minimizes this quotient, which has a constant sign. What's the particularity of this function u, contrary to the Dirichlet boundary condition, is that this function that you get here will be positive or negative, let's say positive on omega, but a priori on the boundary of omega, it will not be 0, certainly not be 0, and will not be constant. It will be just like a sheet of paper which stands in the air like this, and will have some trace over the boundary. And at the boundary, of course, you would have this kind of condition. And now here is the question, and this kind of questions so emerged by Polya in the 50s, was to prove that for all domains of prescribed measure, when you minimize the first Robin eigenvalue, you would get the ball. So the ball realizes the minimizer here. Okay, so why there is some interest here? Well, there is some interest because if you prove this, for example, you would get a Poincaré inequality in H1 with a trace term where you get the best constant. The best constant will be the first eigenvalue of the ball. And also this kind of problem is studied by the community of spectral geometry. So people there is interested about the relationship between the shape and the spectrum. And this is one of the questions. And now I will come back a little bit later to what was the problem of Catherine Bandel, but here I started to state it for the first eigenvalue. And now this problem was solved in 2 steps. First of all, it was in 2 dimensions solved by Bossel among C2 domains which are simply connected. And the proof in n dimension came by Danners in 2006 among Lipschitz sets. So Danners proved with the same method of Bossel in n dimensions that the ball is the best one among all the Lipschitz sets. And the main idea, so which was introduced by Bossel, was to study this kind of function that I will not describe here, and to dearrange it. Now, if you think to the Dirichlet Laplacian and you want to prove that the ball is the minimizer, you would take an omega, you take the first eigenfunction on the ball, it is 0 here if it is Dirichlet boundary condition, then you take the ball here and you rearrange the level sets of this function into disks, and then you would get a radially symmetric function, and you know in this procedure the L2 norm of the gradient decreases and then you immediately compare them and you prove that the ball is better. This kind of argument simply doesn't work for the Robin Laplacian, because for the Robin Laplacian, as the function is not constant onto the boundary, you cannot do this procedure, or if you do it, you will not get the decreasing of the norm of the gradient. So the method of Bossel was rather sophisticated, because she introduced this function, which was defined on the level sets of the eigenfunction and for any function phi, which is positive. And she studied this function, and she noticed that provided this here is exactly grad u over u, where u is the eigenfunction, this is constant equal to lambda 1, to the first eigenvalue. And this is easy. But what's complicated is to notice that for any other function, for some values of the levels, this is greater than lambda 1. And then in this game, by a dearrangement procedure, Bossel and Van Danners proved that the ball is better than any domain omega by a direct comparison. But well, this happened in 2006, and some questions remained open. In particular, what is the most general class of domains where this kind of result apply? Lipschitz set or other sets domain with cusp, or I don't know. What happens if instead of the first Robin eigenvalue, we think, for example, to the torsion problem, to the Saint-Venant problem, which is a semilinear eigenvalue. This was exactly the problem of Catherine Bandel at the time. And of course, it remained open the question of uniqueness. Is it true that the ball is the unique solution of the problem? And in fact, we started to attack this problem with Giacomini, and we wanted to solve the general, more general class of problems simultaneously, namely semilinear eigenvalue problems, where you allow here a power q. So if q is precisely 2, we fall into the Bossel-Danners situation. For example, if q is 1, this is a torsion problem. And if q is different, it's just a semilinear problem. The main difficulty is that the h method, the h function of Bossel, doesn't work. It cannot work if the powers here are different. It cannot work. So people try to do this, and there is no way, for the moment, that the h method works in this semilinear problem, in particular for q equal to 1. And this is what is exactly the problem raised by Catherine Bandel 3 years ago. In particular, 1 year later, for the torsional rigidity, Catherine Bandel and Alfred Wagner proved that the ball is a local minimizer. But local minimizer was obtained by just studying the second order shape derivative and proved it is positive. And now let me say the following principle. And here we come to the free boundary problems. If one proves that when one minimizes the first Robin eigenvalue among all domains, one proves that a best domain exists, and this best domain is somehow smooth, then we can easily prove it is the ball. So this is the principle that I wrote here in red. Existence and regularity implies this is the ball. Well, this, for example, can be easily seen for the Dirichlet-Laplacian again. We have here an easy proof, but one can say like this. Can one prove that for the Dirichlet-Laplacian there exists a best shape, and if it is smooth? Yes, and these are the Alcafarelli techniques to prove existence and regularity of the free boundary. Okay, once you have existence and regularity for the Dirichlet-Laplacian, you write optimality, because you are now at the optimum, and for the first eigenvalue, the optimality condition will read du over dn is a constant on the boundary of the optimal set, like this. And then you have an overdetermined boundary problem, because you have the usual equation minus Laplacian u equal to lambda 1 u is 0, and this extra condition, so then you can say, oh, this is a serine problem, and you can get it's the ball. So one may have in mind the same kind of argument. So if you are able to prove existence and some regularity for the best shape for the Robin Laplacian, can we use its optimality to prove it is the ball? Because it's not just any shape, it is the best one, and formally there is an extra information on it. Well, this is the idea. Unfortunately, it's not in this way that one should see it, because if one proves existence and regularity for the Robin Laplacian, when you write optimality, the optimality for the Robin condition is very difficult. It involves curvature, and you will not have an overdetermined problem, which is nice. And of course, the function will not be 0 at the boundary. But one can use another easy trick, let's call it trick, which works, and in fact, which is a little bit more than just extra boundary condition. It's a so-called reflection principle, so which I will just say in a few words what it means. Imagine that this is the best shape, and you want to prove that this shape is the ball. What you would do, you would move a hyperplane up to some point, you split the domain in two pieces of equal measure, and as the Rayleigh quotient, it's an integral quantity over an integral quantity, you split on the left and on the right the integral quantities, you look the ratios, you choose the best one, and then you reflect your domain. Let's say I reflect the left part, I get a new domain, and as you are at the optimum, this is very important, this new domain that you built here should again be an optimum. Otherwise, it's not possible. And being an optimum, you get the following information. The function that you had here, which was the initial eigenfunction of the domain, of the optimal domain, is eigenfunction into the original domain and has to be eigenfunction into the new domain with its reflection. But this means, because of the uniqueness of the unique continuation for an analytic function, for example, that this function here has to have 0 derivative in that sense. And from here you get the radial symmetry, and later on is the ball. So this is the principle. So you see, in this kind of argument, what I want to do is to prove existence, and I do not really care about the smoothness of the boundary. I just want that the problem is well posed and that it is a domain which is open, because unique continuation is done in open sets. Okay, so this is the principle. And now, for the existence point. The existence, well, you work with shapes, and you know, the shapes, there is no topological space of shapes or whatever that allows you to work, to give you an easy existence result. In the case of Dirichlet boundary conditions, the shape, in the Alt-Caffarelli problem, is hidden as being the 0 level set of a Sobolev function. So you work with functions. Here it's not clear. So a tentative to define the Robin eigenvalue problem in non-smooth domains was done by several people, among which Danners, Dancer, Arendt, Varma, Burzi. Because if you want to prove existence, you have to understand the eigenvalue problem on very non-smooth domains. But I will not insist here, this attack is not really good. It is based on so-called Mazia space, which is a closed subspace in H1, and which differs from H1 as, for example, omega is not smooth, as soon as it's not smooth. It's a smaller space, and you don't really get the good eigenvalue, and it has some good properties and some bad properties. But this is not the good idea. The good idea comes from image segmentation problem. And this is somehow a surprise, because in fact, and here you have the so-called Mumford-Schach functional, which was introduced in the 80s, middle 80s, by Mumford and Schach in order to make a segmentation of an image. And the problem, roughly speaking, reads in the following way. You take an image, let's call it here J, and this image is somehow a satellite image where you have a road and some, let's say, a car on a road, and you want to extract some information from it. In which way? By introducing a new family of contours. So instead of this road, you would like to see something like this, and instead of a car, you would like to see something like this. And here instead of this car. And introducing this family of red contours here, and the new image, they propose to do this by minimizing this functional. U would be the new image here, which has to be close to G. Then you have this term here. This term here, grad U squared, is to be small outside the family of contours in red, which is called K. And this means that you don't have huge variation. And then you have a penalty term, which is given in terms of length of this red part. So in this problem, you have two unknowns. From J, you start with an image, but you have a first unknown, which is the family of contours, the red part, and the new image U, which has jumps across those red lines. And then you minimize this. And this is an energy depending on U and K. K is a closed set, and U belongs to H1 of D minus K. Well, this is a shape optimization problem. You can say it where the unknown is K, the first unknown, and the second unknown is U. If you know K, U is trivially obtained by solving this Neumann problem. Okay? Unfortunately, this problem is very difficult to solve like this. So there is no tool to prove existence of a solution K, U, closed set U, and Sobolev function in a direct way. Only under some kind of hypothesis in 2 dimensions this can be done. But in fact, the good method was introduced by De Giorgi and D'Ambrosio in the 80s, at the end of the 80s, by just noticing that if the family of contours here were Lipschitz, and U it's a smooth function having jumps across this Lipschitz set, then the distributional gradient of the function U across the jumps, in fact, has a good decomposition in an absolutely continuous part with respect to the Lebesgue measure, and the jump part which stays on those red lines. And they introduce the so-called space of special functions with bounded variations, which is a subspace in the usual space of bounded functions with bounded variation, such that when you look to the decomposition of the distributional gradient of such a function, there is no this counterpart. So what is SBV, the space of De Giorgi and D'Ambrosio? Is the space of L1 function such that when you look to the distributional gradient of this function, the distributional gradient decomposes in an absolutely continuous part, which acts like a Sobolev gradient outside the jumps, and a jump term which lies on this set, which is defined point-wise. So a function in SBV will have a gradient in this way. And then they introduce the relaxed form of the Manford-Schach function because they say, okay, instead of working with K and U, remember K was the red set there, a closed set, and U a function with the jumps there. You put these two together and you work with only one function U, which will lie into the SBV space, and the set K here is implicitly the jump set of the function U. Okay? And then you have a unique formulation like this with an unknown, which is a function, and where the jumps are integrated inside the function. And Ambrosio proved the existence of a solution. But then some questions remain. In particular, is it true that a function in SBV, which is L1 only, with a distributional gradient with measures, it's a good solution? Otherwise, in other words, is it true that the jump set of this function is closed? Because if the jump set is closed, then we work into the complement, which is an open set, and we refine exactly our formulation. Closed set and the Sobolev function into the open. And the answer was given by De Giorgi, Cariano, and Iacci, who proved exactly this, that the jump set is closed, and U is smooth outside the jump set, and moreover, the jump set satisfies some density properties. This is so-called the Alfors regularity. There was a different proof by Dalmaso, Morel, and Solimini of the same result in 2 dimensions, but later on there was pretty much effort to understand the regularity of this jump part. Okay, and now just a word to say, this is a so-called free discontinuity problem, and there was a new jump in working in this direction with the crack propagation model of Frankfurt and Marigot, which was formulated in a pretty much way close to the Manford-Schach functional, and where the unknown here is the position of the crack, as well, like in the talk of Rodi Katoader. Okay, so let me go to my point. So now remember what we want to do. We want to solve the isoperimetric inequality. Means that among all shapes, we look to the Robin eigenvalue. We want to prove that the best one is the ball. And we noticed with Giacomini that if you work in a Lipschitz set, for example, and you take the eigenfunction, which I said is not going to 0, it's somewhere higher here, and you take an extension by 0 outside, which sounds a little bit artificial, you have a function, then you extend it by 0, it turns out that this function is in SBV, not the function. It's square, it is an SBV. But with this observation, in fact, we can rephrase as for the Manford-Schach functional, our shape optimization problem is a free discontinuity problem. So minimizing the first eigenvalue among shapes of prescribed measure, let's say equal to n, can be rephrased in the SBV framework like this. We work with function, positive function, accept it, u square, it's in SBV. It's not a nice space a priori. Their support has measure m, it's our measure constraint. And here we have absolutely continuous part of the gradient. On a huge part, it will be 0. So here we'll have 0. I have beta integral over the boundary of u squared. Well, you have two traces on a jump part. Huh? You have u plus and u minus, and you have to add both of them. In the case of Robin, if you have a smooth domain, here is your eigenfunction, here you have one trace, but here you have 0, so you don't see it. Say it was u squared over the boundary, but in fact comes from u squared plus 0 squared. So the good formulation is with these two terms, and you divide by the LQ norm there. And then you want to prove that this problem has a solution and it is smooth, in a certain sense. Well, for the existence of the same arguments of Ambrosio, and because we are working in Rn together with a concentration compactness argument, gives existence. So we can prove existence quite easily. Unfortunately, at this point, the solution, it's a function u, which is 0 outside this very huge set, but this function, it's an SBV function. So we would like to prove the same kind of regularity as the Giorgi, Carriero, and Leacci. Unfortunately, the Giorgi, Carriero, and Leacci result doesn't work in our case, because in fact they proved their regularity result for the so-called quasi-minimizers of the Manford-Schach functional, where you had to compare locally this kind of energy, which involved precisely the Hausdorff measure of the jump. While we don't have this, we have this term over the jump set. And for this kind of term, the Hausdorff, the length, the Hausdorff measure of the jump set may be infinite if this was small, for example. And here started the work with Stefan Lukaus 3 years ago, because in fact we attacked this problem, and the main idea was to replace the quasi-minimality property of the Giorgi, Carriero, Leacci by something which is much weaker, and that we called almost quasi-minimality, in the sense that we compare a function u, we compare this energy, but here on the right-hand side, we allow a quantity which may be larger than 1. So we give some room between this and this. If lambda is 1, we are back to the Giorgi, Carriero, Leacci. If lambda is greater than 1, it's much weaker. And in fact, we proved with Stefan Lukaus monotonicity formula, which works for almost quasi-minimizers. And this monotonicity formula reads in this way. So this is the usual energy, Dirichlet part plus the jump part, divided by Rn minus 1. This is the residual part, which is there to absorb the G function into the Manford-Schach. This is quite easy. But here we have a truncation with a constant which depends on the dimension and on lambda. And we prove that this quantity is not decreasing on a segment depending on a segment around every point up to the boundary. And this formula is, I think, the only formula for the Manford-Schach problem valid in n dimension. Previously, there was a monotonicity formula in 2 dimensions by Bonnet, provided that the set of jumps is a connected set in 2 dimensions. So here we don't have connectedness, we don't have any restriction of the dimension, but we have this truncation, and this truncation is not so nice here. This, roughly speaking, says that this quantity is non-decreasing when it is small, when it is below a threshold. When it is large, it may be. But nevertheless, even in this way, we have immediately the closedness with the monotonicity formula and the Alfors regularity for almost quasi-minimizers. And we had the second monotonicity formula, where we try to compare to find the ratio between the full energy and the Hausdorff measure part into the energy. Okay, so with this, we didn't solve the problem because we proved sort of regularity for almost quasi-minimizers where we compared quantities with different Hausdorff measures on the left and right hand side. But in fact, we proved with Stefan Luckhaus a second result, which is a sort of minimum principle, which says that if you have this, let's call it free discontinuity or free boundary, the boundary of this unknown set, and you take a look to the eigenfunction, which stays on it, this eigenfunction, which is positive, cannot go and touch 0. Well, if everything were smooth, it's clear that an eigenfunction of the Robin Laplacian cannot touch 0, because if it touches 0, you would have that u is 0. So from du over dn plus beta u equal to 0, you get du over dn 0. And this contradicts the Hopf principle. But here we don't have regularity, so we have to prove it. And we really proved that there exists a constant, always a constant, such that u is greater than or equal to the constant once we are on its positivity set. So this means that our eigenfunction stays between two values. This value alpha, and this is very easy, an L infinity norm of the eigenfunction 1 over alpha. And now we are done. Because almost quasi-minimality allows me to replace the integral of u square, u plus square plus u minus square by these two constants. And what we compare will be Hausdorff measures, not anymore the usual Robin energy. So with this, we prove that the minimizer of the Robin Laplacian is an almost quasi-minimizer. So it is it satisfies the smoothness regularity, I mean open set and Alfors regularity, and then the reflection argument will tell us that the solution is the ball.
What was the argument with the Hopf lemma? Because you don't have regularity.
I don't have regularity, it's just a function, yeah. And I don't have, the boundary is just understood in the measure theoretical sense.
So do you use Hopf lemma?
No, I don't use it. I mean, if I would be able to use it, this would be the argument, but I cannot use it. I cannot use it. So it's a sort of Hopf lemma into a non-smooth setting. Okay, so thank you for your attention.
Thank you.
So if beta is less than 0, what would that be?
That's an open problem. It was conjectured for some years that when you maximize, then the correct problem is to maximize the eigenvalue. The solution is the ball. It was proved recently it is not the ball. Well, you see, for a symmetric problem, it may not be the ball. It is not known existence, or so. It's just known that it's not the ball. So for the P Laplacian, for the moment, we were not able to prove the monotonicity formula. I think it's true, but the same problem for the P Laplacian, I think, can be solved. Instead of the monotonicity formula, we are working with Giacomini. We can refine the Giorgi-Carrero-Lacci argument and do it for two different constants. And then the same works.
Okay, if there's no further question, we have 10 minutes break and we reconvene at